Dr. Steve Running. I'm sure everybody online and here knows him, so there's no need for introduction. So I'll just let him take over.
It was fun to watch John's speech that just before me, and I think before I launch into my history and my talk, I guess I want to reflect a little bit for the students about just how much fun it was for me coming as an ecologist to then start interacting with geographers like John and Chris, and then meteorologists like Dennis Baldacci and Inez Fung and systems modeling. For an ecologist, when I think of what my career would have been if I just stayed purely in ecology, I'm sure it just wouldn't have been as interesting. No two ways about it. And John pointed out the one thing that I still remember, and he obviously does too, as we first started interacting actively on the Motus land team, and I was getting ready to build my algorithm for the Motus GPP and PP. And of course, what I considered a routine piece of information was the global land cover. And so it specifically was that 1991 paper that John mentioned that was such an incredible eye-opener to me. And John and Chris and I talked about this for years, actually, as we sorted out what to do, because I was astonished when he said, well, we think we might know global forest cover to plus or minus 10 million square kilometers. And I was just incredulous that here I thought that was basically just a routine input into my thinking, and yet it was valuable for all of us to understand that this component of our understanding of the Earth system had to start with land cover before I could use that as the building blocks to the things that I then did. And when I think about this now in retrospect, some of the most interesting parts of my science have been interacting outside of my discipline with people like John and Chris in geography, not to mention the others that I'll get into as I go forward now. But since he touched on that, I certainly also remember that quite well, how just amazed I was that global land cover wasn't routinely understood. All right, so with that preamble, and maybe, shall we say, handoff from John's talk to mine, I'll get into my history. It's in some ways was similar, and particularly, well, okay, let's get going here. There we go. One of the things you're probably seeing with all of us speakers is that there was no Earth system science when we were in graduate school. None of this thinking existed yet. And so, I mean, here's a picture of me doing my master's thesis work in 1973. And I was trying to figure out how evergreen trees control water deficits, and literally what the stomatal control was for enduring hot, dry summers. And I did not have any background in remote sensing at all. And in fact, when I think about it and we think through the timeline of some of the key components of Earth system science now, when I started graduate school, there were not only no satellites, but there were basically no computers either. As John mentioned, the very first computers started arriving on the lead campuses maybe in 1967. I was at Oregon State University, and I remember we got one mainframe computer back then for the entire campus, and you would walk across campus with a box of a card deck of your computer program, and boy, you didn't want to trip and and drop all your cards. But one of the things that I remember so distinctly is you would go put in your little program, and it would take 24 hours for it to get in the queue and be executed, and there'd be this big line printer output come back. And if you had one single period off on one line of code, it would just abort the operation, and all you would get was an error message, program aborted, and you would have no idea why. And that would take 24 hours to learn that. And so the turnaround time of every single bit of computer program we did was so glacially slow compared to what we do now. But it was, for an ecologist, I was probably one of the really first ecologists to pay any attention to computer programming at all. Because ecology at that point was still quite a descriptive science and quite a reductionist science. If you looked at a plant you wanted to dissect, like I was doing with my master's thesis, you wanted to dissect the stomatal control dynamics, and that's the sort of science that was just being started. I mean, the very fact of having electronic instrumentation in the field was only barely being started. The little gizmo you see on the screen there was a homemade gizmo in a lab just to measure leaf conductance. And so there really, at that point, was no global scale thinking in ecology at all. In fact, I still remember the first estimate of global net primary production was done by a geographer, Helmut Leith, and what he basically took was weather records around the world, came up with a one-line regression equation between, what was it, actual evapotranspiration and net primary production, and that one-line equation was then propagated to weather records worldwide, and that was the first estimate of global NPP. And so I think probably what turned my mind away from the sort of reductionist or descriptive ecology that was the typical training when I started probably was this first look at computer modeling. And I think the computer modeling gave me a tool where I could then build a little computer model of a system I was looking at. And, all right, come on. It gave me an opportunity to think larger rather than think smaller. And so I mean, this diagram in a way is a diagram of almost my whole career of working my way up in scale from this leaf level measurements that I started with and to a global scale. But when I think about what the key first step was my ability to write little computer models and to be able to explore a system. And so this diagram is my very first computer modeling paper from 1975. It was written in Dynamo, which was an early simulation language. I remember this had 23 lines of code, and it would go through a double compiler. First it would compile into Fortran, and then it'd go through a Fortran compiler. And I remember the first time I got it running. Of course, grad students, you would work all night long. You wouldn't work during the day. And I burned up something like $200 of computer time in one evening, which was about a week of my paycheck. And I was deathly afraid I was going to actually have to pay this. But when I look back now, I realize that probably a pivotal issue was that I got a C in statistics. And so I found that classical statistics for me was not my way of quantifying my thinking, because I wasn't very good at it. And it just didn't fit what I was trying to think about. And I realize now that the very first systems modeling thinking became the tool that I really liked the most, because much like an artist that starts with a blank palette, I could build a systems model of anything at any resolution with any components. I mean, you literally had the sky was the limit for your own creativity of a model of the system you were interested in. Now, of course, you could make some really bad decisions and make a lousy model. So not every model's good, just like not every painting is good. And when I think back, I learned early on a lot of lessons about what made a good model logic and what made a bad model logic. And let's see here. It's and so as I started building my modeling logic, the very first model I had was this thing called Daytrans PSN for daily transpiration and photosynthesis, and that pretty rapidly morphed into Forest BGC, which some of you may have heard about, because that was published in 1988. The flow chart I have up there was the original 1988 BGC flow chart. And when I think about what was important of it in retrospect, it was the level of simplification that I chose, not the level of complexity. In the first generations of ecosystem models, we thought that we had to basically put everything we knew about the system into the model. I literally used the model as a giant data garbage can, is almost what it amounted to. And it turned out that they were just unwieldy, unworkable models. And so I think I learned that lesson early on, that critical simplifications were what made a good model. And so, for example, with Forest BGC, I made a couple of really, in retrospect, critical simplifications. One was to use daily meteorology, because that was available worldwide at every Weather Service station operated by the U.S. National Weather Service, by WMO stations worldwide. And so that was a standardization of my input that was important. I realized to not put a lot of physiology in this model, even though I was a tree physiologist. So I actually minimized my own discipline because I could see that in some ways that there would never be adequate measurements, and to some extent many of the pieces didn't look that important. And one of the things a systems model teaches you is what are the components that are crucial and what are the components that are kind of secondary and even tertiary in importance. And I think that we all, as we start graduate school, we think that what we're working on really drives the whole system. I used to think stomatal dynamics was just everything in ecology, and a good systems model teaches you the role of stomatal dynamics, which aren't trivial, but they aren't driving the whole system either. And so I learned the balance thinking of the system with these early computer modeling, not to overemphasize one component and then underemphasize a lot of other components, like soil physics, which I never took a soils course, but I learned that you've got to have principles of soil water holding capacity and water retention in order to do a water balance like the tree water balance that I showed in the earlier slide. The final key, when I look back, logic for Forest BGC that was the big leverage for future extrapolation was I wanted to simplify the vegetation to be nothing more than the definition of land cover and of leaf area index. And leaf area index actually came out of the ecology. It didn't initially come out of remote sensing, but ecologists back in the 60s had first gotten a sense of abstracting the complexity of canopies by a simple measure of leaf area index. And I had, I guess, the critical intuition that leaf area index was a good simplifying representation of canopy processes and capacities. And this is when the first bits of thinking were coming up that remote sensing might be able to detect leaf area index. And so I saw that potential for the future, that if I build a model leveraged with LAI, then maybe the remote sensing had come along to actually measure that LAI. And right about that period, and John mentioned this in his talk, in the early 1980s, NASA was closing down a lot of its Earth remote sensing, as he talked about closing down AgriStars and these Landsat-based studies. And so there was a period when NASA was looking around, and actually President Ronald Reagan encouraged NASA to go find some new science to do. So in this weird way, I probably owe Ronald Reagan some sort of credit for launching my career, because it was NASA that then got interested in global ecology and started looking around. How are we going to do global ecology, of which, as I say, there is absolutely nothing established at that point. They called my old major professor, Richard Waring at Oregon State, to talk to him about getting engaged, and to my enduring good luck, Dick, rather than getting involved directly himself, he said, you know, my old student Steve Running is the one that you should really talk to, because he's been thinking and doing modeling in ecosystem theory, and I think he's primed for new thinking. And so that one moment when Dick Waring handed me the baton, so to speak, and NASA called me to start the planning that became the Earth Observing System, which was in 1981, that we started the very first committee meetings just trying to explore what we might be able to do at a global scale with remote sensing. And so this first thinking in pre-EOS was starting up as I was separately building these first ecosystem models. One of the things that I very quickly came to mind as I imagined looking at ecosystems across the whole landscape was that we couldn't just put up weather stations everywhere. And so one of my little sidelights that I never thought would have much endurance was this little program called Mountain Clim for a mountain climate extrapolator, where I simply would start with observed weather station records from standard weather stations, but then I built the logic to extrapolate it up into complex terrain. And so the slide I have up now is an example from a much later development as we got into DayMet, which many of you maybe know about, and we're still doing this work of taking station data and extrapolating it across complex terrain. It's a different look at large-scale climatology than you get from a GCM, because it's based entirely on the surface observation network. And but it started back from my ideas in the mid-'80s that in order to run an ecosystem model over a large area, I couldn't be just measuring, putting up weather stations everywhere. So this modeling was, my thinking of scaling up my modeling was getting started simultaneously with NASA starting to explore EOS. For a little bit of history, this is what my first big computer system looked like. The numbers involved in the capacities of these computers are just a complete joke nowadays. They really are. But at the time, it was state of the art, and it reminds me that we could have never developed our satellite-driven Earth system science without the parallel development of computing. If we were still back in computing systems of even the 1990s, we couldn't do our science now, even if we had all the satellites up that we have. And so the parallel development of both of those disciplines has been essential. Now, this is my my favorite picture of this talk. You might recognize your host here. This was the day of his PhD defense of Dr. Nemani, before he became Dr. Nemani. And I guess he was my very first PhD student. And I'd have to say I've never forgotten how amazed I was that a kid from a little village in India would have the courage to get on an airplane and fly to America back in the early 1980s and just walk off the plane into a whole new world. I remember Rama telling me that when he got here, he not only had never driven a car, he had never ridden in a passenger car. And so he came so far from a little agricultural village in India to being, you know, a NASA guru that he is now, that I still, I'm amazed by it. And so Rama was my first PhD student, and he's the one that really provided a lot of the computational muscle for these ideas that we're starting to get going. Now, the way I thought of remote sensing, I realize now, was very different from what the classical remote sensing people of the time were doing. They basically looked at a final image as the final product, like a Landsat image, maybe a land cover. Because of my modeling experience, I looked at the remote sensing as another stream of inputs. And I don't think anybody else had thought of it that way back at that time. Is that the satellite data to me was just like the weather station data, and so it was meant to drive my ecosystem model. It wasn't the final end product in itself. And so I was beginning to think about how I could use remote sensing. We were on the way to getting Leaf Area Index by satellite with Dave Peterson, an old scientist at NASA Ames that's since retired. But a really key step was meeting Larry Band. And Larry Band, many of you probably know, was a geomorphologist, I think is what he calls himself by trade. He's at North Carolina now. But Larry was doing some of the earliest modeling of digital terrain data to build a digital elevation model. And the minute I met Larry, I realized that these DEMs would become the template of the landscape for my type of forest BGC modeling pushed across in the whole landscape. I couldn't just operate it on some conceptual flat surface. And so Larry's thinking perfectly meshed with mine. And so we started probably in about 1983, if I remember right, with what became RESIS, the Regional ecosystem simulation system. We then morphed that into the regional hydroecological simulation system, the little flow chart you see there in front of you now. And you'll notice that there's climate drivers of the daily meteorology, there's vegetation drivers from satellite sources, there's the topography and the analysis of the landscape that Larry provided, and then there's soils data, and those were all the driving components for the modeling that I envisioned and that we were working on, and Rama was furiously programming on these primitive little computers. And in 1986, we did successfully show mapping of leaf area index with Landsat Thematic Mapper over Oregon with Dave Peterson at the time. And so we were turning the corner into really having a remote sensing driver for the ecology. Now, a lot of times in these historical summaries, all you hear are the things that worked. And I can't help but throw in a couple of slides of some of the early remote sensing that didn't work. This was a study we did with an airborne imaging spectrometer from JPL, where the thought was that you could directly detect vegetation stress. And we went over to Germany and ended up doing this spectrometry from the top of this ladder truck. And to this day, I'm amazed. That ladder truck had no other bracing or support at all. And when I think of that ladder truck being on top of it, that's what it looked like, I still can't believe why it didn't tip over and be the end of me. The short answer, though, of course, is that we couldn't directly detect vegetation stress with imaging spectrometry after 2 or 3 years of work, and that's something that's still being worked on, and we may finally be getting somewhere. But not all experiments work, that's for sure, and you've got to be willing to face that. I think the papers we wrote on this AIS study were some of the papers we wrote with a negative result. Hey, we tried this, it didn't work, we don't recommend anybody else wasting time trying it some more. If there's any one eureka moment of my whole career, it's this slide. As you heard from John Townsend, in the early 80s, Jim Tucker had started exploring the NDVI. It's funny that Jim and I overlapped at Colorado State University for a year or two and never knew each other until later. And we both laugh about that now. But I didn't know him. I didn't take any remote sensing courses. At the time, I was a tree physiologist. But as I first started being invited to these NASA meetings, of course, this is when Jim and John and Chris Justice and Sam Goward and the team at Goddard were doing those first global NDVI data sets. And I remember I still have actually my copy of the paper, the issue of Science, where they had the cover of Science with that African land cover that John referred to. I've still got my copy because it's hard for us to realize that we had never seen the world before until then. The humanity had never seen the Earth looking down until these first global data sets started to be developed. And I've never seen such complete domination of a field as the Goddard Jim Tucker crowd had of global remote sensing at that time. They had a paper in every single issue of the journals. Nobody else could even do this. So they dominated this field so completely it'll probably never happen again because they were the first to put together the processing system to do it. And but what I was able to do was get Jim Tucker to send us some of this global NDVI data. And so Rama and I started looking learning how to work with this NDVI data. And I then got the idea to do a number of test sites, and this one graph shows Madison, Wisconsin. I got the daily weather records for these test sites. This was in a paper that came out in 1988, but we were doing this in 1985 and 6 is when we were starting it. And so I got the idea, why don't I just run my little Forest BGC model for these sites and then just compare it against Jim Tucker's NDVI data. And I still remember the day. I was in Canberra, Australia on sabbatical, and Rama was up here in Montana doing his PhD work. And he must have had to mail me the data set, because this is long before email. And so he probably mailed it to me on, who knows, some kind of a floppy disk, the NDVI data sets for these. And I was in a little early version of an Excel spreadsheet program, and I ran my little Forest BGC, and I laid the NDVI data set down, and I popped this graph that you're seeing right now up. And right then, I knew that remote sensing of vegetation, there was something big there, because it implicitly tracked the basic growing season dynamic of this Madison, Wisconsin site on its own, with no tuning, no fiddling. I mean, it tracked what my model was telling me about seasonality of photosynthesis and transpiration just straight away. And at that point, that literally, that eureka moment for me said, okay, this NDVI stuff is worth paying attention to, figuring out, and getting into big. And so that's about the time we started really getting serious about working with AVHRR and getting ready for what turned out then to be the MODIS proposal. So as we started working, this would be the late 80s, to this kind of logic of getting net primary production as this array of data layers. And our very first paper, this was the first color remote sensing based image in the journal Ecology that they'd ever published. So this was 1989, and so this was part of Rama's PhD thesis, actually, and it was our first attempt to put together this Rhesus package, drive Forest BGC across the landscape with a satellite-defined leaf area index, and get output of evapotranspiration and photosynthesis. And so this was our first real deliverable, that this idea of driving an ecosystem model spatially with satellite data would work. Now, just for the fun of it, give you a look at how we can look at this same landscape now. This is what we do with MODIS with the 250 meter data set over that exact landscape of that previous slide. So we really, needless to say, come a long ways in sophistication. Now, moving on to our MODIS work, which is probably you're most familiar with. The key logic of that is, of course, the APAR equation of absorbed PAR radiation relating directly with a conversion efficiency to net primary production. And John Monteith was actually in India when he thought up that idea as a simple shortcut for crop modeling in India. Now, implicit in that logic was that you had a crop that was not water limited, and it was only growing during the growing season, so it was not temperature limited at all. So Pierre Sellers had written a couple of very pivotal papers connecting APAR logic to spectral indices in 1985 and 86, as I remember. And so I hopped on that logic to write the proposal for the Modus NPP Mod 17 as it's known now. And yet I knew for it to be operated globally, it had to have cold temperature controls that the Monteith logic didn't worry about at all. And it had to have some sort of water stress definition because, again, his original logic didn't have any. So the proposal that I developed then for the Modus Science team was to do first leaf area index and then this daily gross primary production and annual net primary production from the APAR logic of John Monteith, but modified with cold temperature and water stress limits. Now, John Townsend has already, well, let me digress first. The graph you're looking at there, I want to make the point that this is basic plant physiology just translated to a global scale. In a way, this was my early training in physiology coming to a global scale with simple light, temperature, and water limits on an ecosystem, and really nothing particularly theoretically profound about that. So successfully wrote the Modus proposal, and as I remember, NASA got no other proposals for any advanced products beyond NDVI. And so I really had no competition, if you can believe it now, for this original Modus Science team selection. Now, of course, we then had in 2000 and 2002 our Terra and Aqua launches, and there's Rama at the launch of Terra. And to just move forward, we then have, ever since then, been calculating annual net primary production of the planet and trying to understand the patterns and the regional dynamics of that data set. And so I mean, you probably, most of you have seen these sort of global images from our papers and things like that have arisen from this Modus work. A couple of things that I want to point out about this work is one of the things is it became really clear early on to me that phenology is a big deal. Being able to quantify when the ecosystem turns on for the growing season, turns off at the end of the growing season, but do it with globally generalized logic is a really big deal. And it's something we still can't do well enough with optical sensors because particularly of cloud cover. One of the things that it took me into was the microwave sensing of freeze-thaw logic that we're going to be able to explore with the SMAP sensor that John Kimball in our group here is leading now in a launch in another year or so, where we can hopefully do better at quantifying globally when the system turns on and when the period of growing season activity is and when senescence is, because that is absolutely fundamental to ecosystem dynamics, and we just don't do it well enough yet. And the freeze-thaw measurement really gives you a hydrologic on-off switch for ecosystems that is not cloud cover constrained, and I really look forward to being able to do that. I think the other thing that I want to emphasize now is that right about, well, it was before launch. It was actually in about 1995 that I was spending a lot of time with the International Geosphere Biosphere Program. I was co-chair of one of the working groups, and I was meeting these meteorologists that were just starting to perfect these eddy covariance flux towers. And I particularly remember a meeting in La Tuile, Italy, and my two turned out longest colleagues, Dennis Baldacci and Riccardo Valentini from Italy. And we started imagining how valuable it would be, number one, to have these coordinated flux towers worldwide. But it became clear to me that those flux towers would become just automatic validation points for my MODIS data set, because my MODIS data set was covering everywhere on Earth. So any place anybody had put a flux tower, I would be able to use that flux tower to see if what I think that pixel was doing was the same thing as what that flux tower was doing. And I can't overemphasize how critical to the acceptance of the MODLAND advanced biophysical data sets that FluxNet has been. Because with that hard ground level validation for sites worldwide from different biome types with all different seasonalities and dynamics, to be able to test our MODIS data sets against those flux towers, I think is a major part of why these MODLAND variables have the credibility they do. And I have to emphasize, when I wrote my original proposal in 1999, nobody had even thought of flux towers. So the whole idea of a flux tower sitting in a landscape, and the way this diagram I'm illustrating here, and MODIS quantifying the entire landscape, and then having this flux tower sitting in the middle of it, and the scaling, the multi-scale analysis of that landscape with the towers on the bottom end and MODIS on the top end is something that I think has been just pivotal to the success of the MODIS data sets. And it really was never planned at the beginning. And I think it illustrates one of the things that's so powerful about these international consortia like John Townsend mentioned. Things like IGBP and GCOS are the only way you coordinate things like that globally. There's no way just one by one we could ever do things like that. We ended up with having 4 of these global vegetation workshops here in Missoula, where we really put together the remote sensing crowd and the flux tower crowd, and we hope to have a 5th one in another year or so, because I really think that that's an important part of this multi-scale science. Now I need to get going here, and so I want to turn a corner here in these last bit of slides and talk more about how we relate our science to the broader world. And one of them I'll start with is kind of a bit of toy science that we started with, illustrated here. We started looking at the MODIS land surface temperature just kind of for the fun of it, to see where the hottest place on Earth was. I'd been out in West China, and they claimed it was the hottest place on Earth, and we started just putting it together. This was not theoretically advanced science at all, and yet when we started publishing papers on it, the public really picked up and continues to pick up on this little bit of kind of publicly translated science. And it taught me that you don't have to be cutting some new theoretical ground to do things that are quite interesting to the public and help them understand the science they're doing. When I look forward now, I think we need to be looking towards the kind of thing that I'm showing here, integrating all our pieces of capability into a terrestrial carbon monitor. And I wish the politicians had more serious interest in this. In GEOS, which John mentioned in his talk, we've actually planned this out in a pretty complete way, and yet we're not in any way getting the final, I guess, the final funding and coordination to go do it. And as I look into the future, the global carbon monitoring is going to be more and more policy relevant, and we've got all these pieces, but we haven't assembled the entire engine to do it. I think more generally, we've got to think more about how we package some of our science so that the public and policymakers can understand it more. And I use this example that I show here of the IGBP Climate Change Index, which I conceptualized and a team of us put together for IGBP over about 3 years. The components of it are all direct scientific measurements that the scientists were already looking at. But I realized that the public couldn't necessarily assimilate all these pieces in the way we needed. So we came up with this climate index logic purely to help the public understand the science better in a simple and graphically easy way. And I just think we have to, as scientists, spend more time doing things like that than we have in the past. And certainly more time than I ever thought I'd worry about when I was in graduate school. I'm seeing that we've got to get way more engaged in the policy world. And probably a lot of you are cringing as I say that. And yet I just don't see any way around it. What I've put up here now is the planetary boundary diagram, which a paper in Nature in 2009 introduced this just before the big Copenhagen COP summit. And it's a translation of Earth system science that isn't quantitatively precise yet, but the policymakers could really understand. And it's taught me that we need to start working harder to translate the details of our science into more simple, conceptual and visual and graphical material like this, or else we're just not going to get the connection that we need. And one of the things that, as one more example that we're working at, is we're now starting to look at our NPP as a measure of bioenergy, and we're trying to put together all the components of the global carbon cycle. And what I realize from that is, while we do that detailed science, we have to come up with nice visuals. I like to hope this is a nice visual of the partitioning of global NPP on an annual basis, because we then have to be able to take this to a policy level, or else our science just isn't going to make the difference to society and the world that we know it needs to do. I'd have to say I'm pretty concerned about the state of the planet right now, and I'm not so concerned that humanity couldn't think our way out of our problems. I think we could. I'm concerned with the lack of leadership and vision and political cooperation globally to make it happen. And so no amount of our clever science is going to be good enough if it doesn't propagate up into very high level understanding and decision making at the highest levels of all of our governments. And I'm just afraid that you, as Earth system scientists starting out, are going to have to be way better at that sort of connection than we ever worried about when I was in graduate school. And to echo one point that John Townsend made, I think the social sciences we now have to be very actively engaged in, because we're talking about human decision making and human preferences, and we're talking beyond the biophysics into what humanity decides to do with the planet over the next century. And so I really think that what you need to do now is take the old timers like us and sit us out to sit around and drink wine together, and I think you all need to take over as soon as possible. And so I wish you well in doing so, because I'm afraid our generation, we've laid a lot of scientific foundation, but we haven't figured out how to influence the policy dynamic in a way that is needed, and I think that's something you all will have to learn how to do. And I think I'm way beyond what I should have taken, so I better end now and take any questions you have.
Thanks, Steve. That was fantastic. And I think the iPad really made the difference.
Oh, okay, good.
Hi, Steve. This is Jennifer.
Hi, Jennifer.
So I thought I'd field some questions from the chat room as well as inside this room. Probably the first thing I wanted to start with was Amanda Truitt in the chat room. She's asking. She really likes the slides that you were just expounding on, the last few slides. She's wondering, are they available to use to promote this work?
Definitely, I think everything I showed has been published. The terrestrial carbon monitor, certainly the IGBP climate index, and so I guess also, aren't all these talks going to be, the planetary boundary image is part of the Nature paper, and the final slide there of the global NPP partitioning, I submitted a little perspective note to Science on that yesterday. And so we all know what the chances of that are, but I had to give it a go. So I think all these last half dozen slides are available and have already been published in other places, yeah.
Great. So this person, Amanda Truitt, says she's teaching earth science to policy majors, so she'd really like to use them.
Yeah, and I think, to reiterate, we don't have the luxury of just sitting quietly in our labs doing our science the way I did when I was in graduate school. The planet's not going to last that long if you all don't really get engaged.
Any other questions in the room?
I guess I've got a question about that engagement with policy, and I guess the question is more or less just how to engage. So would it be through the type of proposals we're putting together, or is it through communication of our research better, or what kind of engagement?
Well, yeah, I can tell you that in the international global science circles, like the International Geosphere Biosphere Program, they're already actively trying to lay a foundation for more integrated biophysical and social science research. And yet, that really is an umbrella. At the more hands-on level, we need more integrated proposal calls from our agencies, because I think we all know we end up doing what we get funded to work on. We just can't afford to do anything else. And I think our agencies are only getting started in how to put proposal calls out that effectively draw this kind of thinking. I think the other thing is the culture of the social sciences is so different from the culture of our natural sciences that it's going to take a long time. And I say this with my own daughter being a PhD student in environmental sociology. And so I see this within my own family, that the way they frame questions, the way they take data, the way they analyze data is very different. And all of us are going to have to work at learning each other's cultures and methodologies before we can get started. And I'd have to say in the 1980s, this is exactly what the ecological sciences did with the physical sciences. And so I've already seen the marriage of disciplines in my own career in that regard, and I think we're now on the threshold of a next one of these major marriages of disciplines for earth science.
Thanks, Steve. I wanted to shift gears a bit. Gordon Green asks, what is your sense of the relative importance of new vertical global canopy characterization via LIDAR and radar? Do you think this additional data will improve GPP or NPP estimates significantly?
I I think it's a long time before it'll make much difference for our global scale calculations, but I think that type of methodology, some of the new canopy stress methodology, has promise for more regional and local scale remote sensing in a pretty immediate way. I mean, what they like to call the APAR logic is what? They derisively call them green slime models, where you don't differentiate any canopy structure at all. And I think that logic's now been around for 30 years. And so it's certainly time for a next generation of thinking there. But at a global scale, it's going to be a long time before that matters. But it's certainly at a more local scale, it could be a good step ahead.
I had a question, thinking over the long term, that some of the major ideas that have emerged in Earth system science, such as the CO2 fertilization factor and single values of stomatal conductance over really large areas, or heretofore unsuspected carbon sinks in large regions, essentially use global ecological behavior as a residual term, as a way to close the budget. Do you have faith in that kind of approach, or do you ever suspect that vegetation dynamics are being used to hide or cover errors or uncertainties in other parts of the system?
Well, one of the things I first realized when I did some of the first global photosynthesis calculations was the neat thing was that nobody could prove you wrong. And so it was from direct ecosystem measurement, we only have the ability for measurements at kind of the flux tower and small regional scale. We then have to completely flip the problem on its ear when we go to either atmospheric CO2 inversions or to things like our optical remote sensing driven things like GPP. And so it's a classic bottom up and top down connection that you end up having to make in order to have confidence in either direction at a global scale. And the tough part, I sometimes laugh to my students about this, is we work towards the final calculation of, for example, global NPP, but if we ever get the right number, we won't know it because there's really no... Think about it. There's no secondary way to verify exactly that your calculation is correct. We really try to bound in these calculations from multiple directions with multiple technologies. And so in effect you squeeze in the uncertainty, hopefully, to finally this cluster of where the truth has to lie. And there's just no other way to do global scale calculations because there's the measurements you take are at so many different scales in space and time and methodology.
Well, thanks a lot, Steve. I think we have to end here because we're going to move along to the 11 o'clock scheduled talk. So we really appreciate your contribution today.
All right. Well, good. So I think I logged this out, right? So you can log the next one in.
Yeah.
Okay, here goes.
Hi.
Thanks a lot, you all.
Yeah.
Bye.
Thank you.